This is a little overview of the development of Graham's law that I didn't take time to do in class today. So I decided to show this video that someone else did. We'll have a few comments as we go. Notice the nice music.
Hello. In this video, we are going to derive Graham's law of diffusion from the principles of the kinetic theory of gases. First, we assume that we have two different gases in a container, gas A and gas B, and that they are in equilibrium.
And that they are at the same temperature. So if they're at the same temperature, their kinetic energy is the same. Remember, temperature is average kinetic energy.
Therefore, since they are in a thermal equilibrium, they have, by the kinetic theory of gases, the same average kinetic energy. So the average kinetic energy of A is Ke sub A, with a line over top of it to show that it's the average, is equal to the kinetic energy of B, average. Next, we use the formula that the kinetic energy is equal to 1/2 mv squared. So on the left-hand side, we put the appropriate...
So it's 1/2 of mass times the velocity squared. It's another formula for kinetic energy. 1/2 mass times velocity squared. They left out the 1, or the guy left out the 1, because 1/2 is really just this number divided by 2.
Subscript, so we have the mass of A times the velocity of A squared divided by 2. That's the kinetic energy of A. And then m sub b v sub b squared over 2 is the kinetic energy of gas B. Next, we multiply each side by 2 to get that m sub a v sub a squared is equal to m sub b v sub b squared.
Remember, as long as you do the same thing to both sides of the equation is still true. So if you multiply both sides by 2, the 2's cancel.
Now, if we divide each side by m sub a and v sub b squared, we get that v sub a squared over v sub b squared is equal to m sub b divided by m sub a. If we take the square root of each side, we get that v sub a divided by v sub b is equal to the square root of m sub b divided by m sub a.
This is where I went in class today, for those of you who are in class. Velocity 1 over velocity 2 is equal to the square root of mass 2 over mass 1.
Next, we can multiply the right-hand side by the number 1 in the form of the square root of Avogadro's number divided by Avogadro's number. So note here that the subscript A refers to Avogadro, whereas the subscript for the red symbols is for the gas molecule type A. Now note, if I multiply the mass of one gas molecule A by Avogadro's number, I get the molar mass. So this is a slightly different m, kind of written more as a script. So here the m sub a refers to the molar mass of gas molecule A.
So actually, here's where I got to in class today, because I didn't tell you about this step. We just went straight to molar mass. So you don't need to worry about this particularly. It's just that you multiply by 1, and this is the molecular, the number of molecules in a mole. So if I took a mass of one molecule and multiplied by a mole of molecules, then I'd have the mass of 1 mole of molecules. And a mass of 1 mole of molecules is called the molecular mass.
Similarly, if I multiply the mass m sub b of one B gas molecule times Avogadro's number, I now get the molar mass of B. So now we see that the ratio of the velocities of A and B is inversely related to the square root of the molar mass of B divided by the molar mass of A. Finally, at the point of effusion, the gas molecule A inside the container and outside the container are in thermal equilibrium. So they will have exactly the same velocity by the reasoning that we used up here. So we can replace V sub A by R sub A, where now R sub A is the rate of effusion of gas molecule B. And by the same reasoning, since the gas molecules B are in thermal equilibrium before and after effusing, the velocity is exactly equal to the rate r sub b. So we get our final conclusion here, Graham's law of diffusion, that the rate of diffusion of A divided by the rate of diffusion of B is equal to the square root of the molar mass of B divided by the molar mass of A.
So the relative rates of effusion, so let's get his hand out of the way. So the relative rate of effusion of gas 1 to gas 2 is inversely proportional to the square root of the molecular mass of the gas 2 to gas 1. So it's inversely proportional to the square root of their molecular masses. Inversely means they get flipped.
I thank you very much for your kind attention. Stay safe, and as always, have a good one.